So let's start with the course in earnest. We are going to cover, broadly speaking, rock types and the rock cycle. So the obvious first question is, what actually is a rock? You all have seen rocks, but how would you actually define what it is? And we see here a number of characteristics that tell us what rocks actually are. They are coherent, so it is a solid material, a hard material. It is naturally occurring, so if you would make concrete that is has very similar features like a rock and even very similar composition like some rocks, this would not be a rock because it is not naturally occurring. All natural rocks consist of minerals, of individual particles, which are essentially crystals, and most rocks consist of more than one mineral species. There are some who have only one, but usually you will find more than one mineral species in any kind of rock. Less commonly there is glass. That is material that you will find in volcanic rocks. Glass is a quenched melt. It is melt that was cooled down so quickly that it could not crystallize, but also that might be part of a rock. And if the volcanism is explosive, glass fragments might be present. But that is an exception, only in the volcanic type of rocks and in very few others. Here we see a microscopic image of a rock that is across perhaps not more than 2 or 3 millimeters wide, what we see here in the field of view. And you see here these roundish grains. These are sand grains. They consist of the mineral quartz. And we can see here from the shape and the very beautiful roundish shape of this here, for instance, we can see from the shape that these are grains deposited in a sediment originally. But we see here in between these former sand grains, we see these spaces are filled with other minerals. And these minerals, they form the cement that give the rock coherence, that make it hard. You know that a sand, a beach sand or a river sand obviously is a soft material. It is incoherent. Rocks are coherent and therefore they require, if they are sedimentary rocks like this one, they require a cement that makes them hard, that gives them coherence. We see here a graphical picture of the situation with sand grains and other minerals in between that are called the cement. That can be different material. It can be carbonate, for instance. It can also be SiO2 and quartz crystals that have grown actually in these former spaces in between sand grains. And this pore space must be filled with a cement, otherwise you would not talk about a rock. In magmatic and volcanic rock, that is slightly different. There you don't have sand grains deposited. We are going to talk about how magmatic and metamorphic rocks form. But for sedimentary rocks, this is a pretty good representation that we see here. If we know that a rock is coherent, naturally occurring, a solid, and it consists of minerals, the next question would be, what actually is a mineral? A mineral also is a naturally occurring material that has a crystalline structure. And a crystalline structure means it has a specific orientation and spatial arrangement of the atoms that form this crystal. And we see here the crystal halite. Here we see an image of it, how it looks macroscopically. And halite is simply salt, sodium chloride. You use it every day to season your food. And here we see that sodium cations and chlorine anions are present in a specific proportion, 1 sodium per chlorine anion. So both of them are abundant in equal amounts. And the sodium cations and chlorine anions are connected to each other in a specific orientation with a specific distance to each other and in a regular sequence of sodium and chlorine. This here is another representation. You have seen all that in your chemistry lessons at high school. This is what a mineral requires. It's a crystalline structure made up by a homogeneous chemistry, a chemical composition, in this case here sodium chloride, with a well-defined spatial orientation of the atoms to each other. So not all crystals are as simple as the sodium chloride, the halite. That would be the term for the mineral. There are others that consist of SiO2, that would be the mineral quartz. Here we see sodium, aluminium, silicate, that is the mineral albite. And in albite, we have again a very specific proportion of sodium to 3 aluminium, 1 silica, and 8 oxygen atoms. Calcite, that is simply calcium carbonate that you find in limestone or in marble. Calcium carbonate again has 1 carbonate group and 1 calcium oxide combined. That will give you CaCO3 as a chemical formula. If these components are present at that proportion and are oriented in a crystalline structure, then this would be the mineral calcite. So these are the minerals, and in a rock you have usually different types of minerals. That is what a rock is. That is what minerals are. We have 3 classes of rocks. There are the sedimentary rocks, the igneous rocks, and the metamorphic rocks. And the sedimentary ones we already had a glimpse of with this sandstone, that sand that got cemented by matrix minerals that have grown in the pore space, in the gaps between the former loose sand grains, and gave it solidity. Similar processes can happen if you deposit clay, so fine-grained material instead of sand, or you deposit coarser-grained material like pebbles or cobbles in rivers or in other sedimentary basins like lakes or in the sea. Then there is a second group of sedimentary rocks, and this second group forms by chemical precipitations. If you think about a glass of water that has a high salt content, you put a lot of salt into it and you then evaporate the water. What will happen is at a certain point, salt crystals will start to precipitate, to grow at the bottom of that glass. And such a process also can happen naturally in salt pans, in lagoons. You might evaporate water with dissolved cations, and these cations might eventually crystallize if water evaporates. Then there are igneous rocks. They form from magma. That means a combination of crystals and melt. That is what magma is. We do not find normally magma that only consists of... Tommy, be quiet. That only consists of melt. Usually there are crystals already present, and igneous rocks includes those which come to the surface and form volcanic rocks, or those magmas that crystallize deep in the earth. These we call plutonic rocks. Metamorphic rocks can be either former sedimentary or igneous rocks that have changed their nature. That means their composition or their texture during changes in pressure and temperature that they have experienced during their evolution, during the history of these rocks. And that is an important observation. All these rocks that we have discussed here, they do form at a certain time, but that is not the end of it. In the rock cycle that we are going to get to know and learn to understand in this lecture, these rocks have a history, they evolve, they might get destroyed, they might get overprinted and change, and therefore become different kinds of rocks. Why do we know all that? We know that from observation. And the first one who made the observation that different rock types exist and have different kinds of ways to form and different features, that allow us to distinguish them with James Hutton. James Hutton lived in the 18th century, and he is probably the most important of the early geologists that started to make natural observations and tried to explain how our planet works. So we owe a lot to James Hutton, particularly the classification of these rocks and the basics that allow us to define and describe the evolution of rocks in the rock cycle. Here we see a natural outcrop of rocks. These are sedimentary rocks. We see a layered structure. When we look at the upper part of this outcrop, we see these horizontal layers of finer grained rock. These are sand layers, light gray in color. Then there are coarser grained layers that we see here, where we see individual pebbles in different colors, white and brown and gray. And there's an alternation between sandy layers and pebble-rich layers. Here we see a boundary, a very sharp boundary, and underneath we see very similar layers, but they are tilted. This allows us to conclude there were tectonics in play. Layers of sediments always get deposited in a horizontal way, and we see here this was once the horizontal orientation in which these layers formed. They later got tilted, eroded along a surface, a sharp surface, and younger layers were deposited on top. This is a process that we will discuss in the first year of geology. We call this an unconformity. You shouldn't be bothered by that right now. Now we need to see here the main characteristic of sedimentary rocks are the changes of material from layer to layer. And we are going to learn that we can conclude from the different nature of the rocks to different environmental conditions at the time when these layers were deposited. So here, a layered sedimentary rock. Here we see a volcanic rock. We see lava that is extruding on a surface. This is probably somewhere on Hawaii. That is a place where these kinds of lavas form, and you see here these rounded surfaces that are formed by older lava flows. Here is a younger one, and here this geology student is measuring the temperature. You see here at the front of the flow, the lava is still flowing. It is red hot. We see here these typical shapes that slowly flowing lava forms. It looks a little bit like the skin of a rhino. And this is the cooling surface while underneath the lava is still flowing. This student here is measuring a temperature, and he will probably measure something between 900 or 1000 degrees. This will be the temperature of this kind of volcanic rock just before solidification. And we see here some volcanic eruptions are relatively harmless. You can go very close to the lava flow and study this material. Other volcanic rocks are formed by much more violent processes, and we are going to talk about that in the last section of our course. Here we now see metamorphic rocks. This is the third big important group of rocks, and these are rocks that have experienced usually deformation under high temperatures and pressures. And this beautiful beach outcrop that we see here shows us there are different rock types. Essentially here light colored rocks that consist of obviously light colored minerals. Feldspar and quartz might be abundant there. And then there are layers of dark colored rocks. And you see here nicely in the third dimension that what we see as color differences here that are not superficial stripes on the rock. This is actually the color of a three-dimensional layer. If you look carefully, you see that this sequence of dark and light colored rocks is actually folded. If you follow here this thin layer towards us, you see that this layer turns around here in a fold, goes up again, and here runs away as this second layer. And this is a very typical feature in metamorphic rocks, folding is one of the important deformation processes. It shortens rock sequences, it stretches them out laterally, and that all happens at high temperature when these rocks are relatively soft. They are not molten at that time, but they are soft, as for instance, a rod of iron might become soft if you heat it up to 500 or 600 degrees. It starts to be glowing red, and a blacksmith can change its shape without breaking the iron, and obviously also in a state where the iron is still a solid. It is just soft. It is not molten. It is soft, and that allows the deformation. The same applies to such metamorphic rocks. At very high temperatures, they get soft, like hot metal would get soft. How can we describe and distinguish rocks further? We can use the physical and the chemical characteristics. We have seen already particle size, we have seen different colored particles, we have looked through a microscope, at least on an image, and we saw the round nature of sand grains and the nature of the cement in between these sand grains. And we have learned a little bit about the composition of minerals, and if minerals have a chemical composition, then obviously also rocks have a chemical composition that is controlled by the composition of the minerals. So these physical and chemical characteristics we can use to distinguish different types of rocks. Grain size is usually measured in millimeters or centimeters of the individual crystals or grains or crystal aggregates or fragments of older rocks that are ending up in younger sediments and then form rocks after cementation. We can use the shape of these grains. We have seen the rounded shape of the sand grains, but obviously other crystals can be elongate, they can be stretched, they can be shaped like a sheet or an ellipsoid, prismatic, needle-shaped. A large number of terms can be used to describe the grain shape, and obviously also the types of minerals that are present. Is this a rock that is formed essentially of halite, the sodium chloride that we have seen before? Is it a rock that is mainly formed of quartz and has some feldspar or mica perhaps? Different mineral compositions will define different rock types. And it's not only the different types of minerals that are present, it is also their relative proportion to each other. Here we see an illustration of a metamorphic rock that gives us some access to the importance of crystal shapes and crystal orientations. We call it texture when we talk about the arrangement of crystals and the different shapes of crystals and the different structures that are formed. We see here a layered rock that obviously also has undergone some folding, and this layered rock consists of dark rocks and light colored rocks in this interlayered sequence. And when we look carefully at a smaller scale, we will see that minerals are in a preferred orientation parallel to these layers. So even at different scales, you will see that layered texture and structure of the rock. Grain size can be measured obviously in comparison to scales, and we always try to quantify our observations in rocks. Of course, we can say a rock is fine-grained or coarse-grained or medium-grained, but it would be better to say, well, the most common minerals in this rock are 0.5 millimeter to 1 millimeter in size. That is more precise because it quantifies your observation. As I said before, the chemical composition is controlled by the composition of the minerals. If you, for instance, have minerals that are rich in silica, then also the rock composition will be silica rich. If you then also have minerals in that rock that are rich in potassium and in iron, then your potassium and iron proportion will increase in the rock. And you can analyze the composition of rocks when you take a representative rock sample, you grind it down to powder, and this powder you homogenize and analyze it in a machine that we call an X-ray fluorescence spectrometer. This instrument will give you the composition of the rock, and this composition will be expressed in the form of oxides, SiO2, aluminium oxide, potassium oxide, and so on. We see here the result of such an analysis. In geology, we always use the oxides because we assume that the lithosphere and the Earth's mantle, that means the most of the Earth, are actually oxidized, and that applies to most rocks. Here we see listed the different element oxides, and here we see different analysis from different rocks that give us different compositions. And we see here these rocks, these are magmatic rocks and metamorphic rocks. They have a high silica content between somewhere in the mid 60s and the lower 70s in weight percent. So for instance, this first sample here has 66.77 weight percent silica oxide. It has much less titanium. Titanium is in most rocks quite a rare mineral. It occurs around 0.5% to 1%, maybe a little bit more in some rocks. But titanium oxide obviously is less common than silica because the Earth's crust and the Earth's mantle consists essentially of silicate rocks. Aluminium is also usually quite abundant. 10 to 20% is very common for most rocks in the Earth's crust. Iron and magnesium together are usually below 10%. Manganese is usually a minor or a trace element. Calcium might be present, might be absent. Here in these rocks, it's about 1.5 to just over 3%. Sodium also can be present more or less abundantly. Around 2% is not too uncommon. A few percent of potassium oxides, up to 5 or 6 in such rocks. In other rocks, there might be less. Rarely there will be more potassium. And phosphorus is usually 0.5% in most rocks of the crust, sometimes less, sometimes a bit more. And you see here the total of all our oxides should come to around 100 weight percent. Usually a little bit less because there are some elements present which are not listed here and which might be present in very small amounts. There also might be water. Usually there is a little bit of water contained in rocks, and that is not listed here, and that explains the difference to 100% in the total results. You're going to work a little bit in one of your practical assignments with the chemical composition of rocks and how we convert these numbers into some more meaningful portrayal in the form of diagrams. But your lecturers will come back to you with that, and you will make your own experience with these kinds of data. And then we have the texture and the structure. Also here we have already seen examples in these layered and folded rocks, particularly metamorphic and sedimentary rocks have usually a layering that shows abundance of minerals in some layer and their absence or scarcity in other layers. How are the minerals oriented in there? Are they randomly oriented? Are they well aligned? Do they occur in little clusters, which might make a rock look a bit spotty? Or are there at all any layers of different composition? Or is the rock uniform in composition and does not show any layering? So these are observations that are at the beginning of the classification of rocks. You will learn that science is essentially based on the observation of features. Observational skills and descriptive skills are extremely important in scientific analysis, and you should work hard towards developing your descriptive skills and your observation skills, because otherwise it will be impossible for you to be a good scientist. So in this lecture, we have been seeing the main characteristics of rocks in general, and we have discussed that there are these three important groups: sedimentary, metamorphic, and igneous rocks. In the next lecture, we are going to have a good look at sedimentary rocks and sedimentary environments. Thank you very much so far.